of discussion along the way, but luckily that means we don't really have that many outstanding questions from the chat. So actually, maybe, well, so the plan is that we will actually stop the official part around 7. I imagine a lot of people would have to leave then anyway, but the room will be kept open so we can keep discussing if some of you want to stay. And now let's maybe start with the topic that was a recurring theme in the conference and actually in the community for quite a few years, which is, well, this discussion between the cosmic string network emitting particles versus gravitational waves. So given that we have Mark Hindmarsh as a panelist, also Tanmay Vachaspati, I thought it would be a good time to actually come back to this discussion. It was raised in questions along the way, because to be honest, I was actually under the impression that with the second point of Danielle's talk and the paper shortly before that, I was myself under the impression that the problem was more or less solved in the sense that everyone was right, but different scales were involved. So what are your thoughts concerning that?
So I guess I was the noisiest during the day on this issue. So indeed, it's well, it depends what you mean by right, of course. But of course, it's sort of the interpretation and the extrapolation of what numerical simulations of classical field theories are telling you. That is, I think, the question at issue. And so I think the thing that no one would dispute is that if you do numerical simulations of cosmic string networks in the abelian Higgs field theory, then you find that the loops of string that are created basically collapse almost as quickly as they can. So if the size is L, then they collapse in time L over C. And you know, and this was we did a sort of a study of this, sort of a detailed study of this very recently. But Kai Schmitz referred to this paper and put it in the chat. There's some nice movies you can see there of on the one hand, a sort of network style random loop collapsing. And on the other hand, it is possible, as Tanmay and his collaborators showed us, to make loops which behave in a Nambu-Goto way. So then, but you have to work very hard, and all network simulations have not, so far anyway, have not made any of such loops. So then the question is, what does a field theory network make any of these loops? As Jose Juan said, a real network in the real universe is making zillions and zillions of loops, and it only has to make a few in order to be interesting. And then the question is, how many does it make? And that is an open question. And at the moment, the number is somewhere between 0 and some fairly small fraction, it seems, from the simulations, which is kind of interesting. It's sort of, you can think of this as another modeling parameter for cosmic string networks. So that's what I wanted to say. Yeah.
I see, but that's not in conflict with the idea that in very late evolution, if the network reaches scaling, it will still follow the Nambu-Goto, essentially.
I think that's what Jose Juan and Tanmay believe. But there's no, put it this way, there's no sign of that happening in the numerical simulations of networks, some of which are quite large, ratio of many hundreds to the string curvature width and string curvature and the string width.
Yeah, sorry, if I may add, I mean, I noticed Mark's paper recently where he said, sort of introduced this other modeling parameter, and I think that might be the way to go. It's where some loops which maybe don't have enough angular momentum or something, and they collapse mostly into particles, and others which have angular momentum, maybe they survive a longer time. And so there might be other things going on. It's not clear to me.
Can I say something? I think the fifth year simulations have done an impressive work of size of the simulation has improved by a lot in the last few years. The problem is that we may be still not large enough to reach enough numbers of loops to see the ones that are not going to decay. One thing that you can say is, if I take a random loop from my network in Nambu-Goto, is it going to be non-self-intersective? The answer is no, by a huge number. So I would have to take many before I get one that is non-self-intersective if I take them randomly. So it may be that it's kind of very hard. It's not enough to go to large boxes and a large loop compared to the thickness, because you can take one of these arbitrary loops, they self-intersect several times, and by the time they get to be small, they of course annihilate. This is all consistent. So I'm saying that the problem is hard, that it may be all consistent, it may be what Tame in some sense I am saying, but it may be hard to find numerically. Or it may be some other dynamics completely that we haven't discovered yet.
Yes, well, I'm glad Tame is supportive of the idea of having this extra modeling parameter. I think it's the only way out at the moment, and then you can sort of see what cosmic string models survive the combination of gamma rays and gravitational waves.
Just a small curiosity, other than the gamma rays and gravitational wave, will the CMB bounds be effective for this new parameter or not? Because it's very late time.
Yeah, I think that's there for more or less for either of them, because that depends basically on the long strings, and there's not so much disagreement about what the density of long strings is, just the lifetime of the loops.
Okay, but then, do you agree with the assessment of the impact of this, let's say, phenomenological part that almost everyone was using in their talks, which is that essentially there will be some sort of cutoff after which the loops loops contribution will be cut.
Yeah, well, I think were you referring to Danny Steer's talk? Is that?
Yeah.
Yeah. So yeah, so I guess in this sort of mixed scenario, the population of Nambu-Goto like kinky loops would behave like that, but there would be an additional fraction which may be much bigger, which would just collapse and make particles, and those would, so essentially most of the total energy of the string network would go into particles, and then that would be constrained by the gamma ray observations. So I think you can probably still get an interesting gravitational wave signal for LISA, even for the things that are bounded by gamma rays. So if you wanted to be optimistic about LISA spotting cosmic streams, it'd be an interesting thing for someone to do.
Right.
I actually had a kind of a question for Mark and Jose and others. So looking at string dynamics, I mean, if you have a loop with a certain angular momentum, do you know if there can be a situation where the angular momentum gets lost gets radiated before the energy gets radiated, and then it becomes a circular loop, and then it collapses, maybe to form a black hole or something? Is that a possible scenario?
Well, I guess for field theory strings, it seems that everything, if they're behaving like an Ambrogotto string, then I would defer to Jose Juan. But if they're behaving like a field theory string, then they just everything is radiated energy, angular momentum within one light crossing time. There's no possibility of forming a black hole, I think.
And in the other scenario with gravitational waves, I mean, I remember doing this calculation many years ago, but
I guess you have to do the calculation of the gravitational waves and back reaction correctly to be able to test how much angular momentum is carried away by the gravitational waves, right? So,
and the rate is the same as that of the energy lost?
No, I think you have to do the calculation separately. I don't know. The short answer is I don't know. But I will add it to the list.
Okay, good. Yeah, maybe I can sort of raise sorry, this is more that I'm raising questions rather than answering them. But might as well, since it's a discussion. So in your gravitational smoothing scheme, Jose, you smooth out the sort of roughness of the loops, but do you also smooth out the velocity, roughness and velocity? Like,
let's see. Because what we do is we go to the description of the loops in the Kibble-Turok sphere, and then we look at the functions A prime and B prime, and then we smooth those functions with some kernel, which depends on the size. So if you smooth A and B, or A prime and A B prime, you're smoothing both the string and the velocity.
Right. Okay.
And as I said, the real back reaction seems to be partially right, in the sense that it seems to see that some roughness gets smooth, but it's not completely right. In some other cases, for example, in the cases of a cusp, and we look at this in the paper with Jeremy and Ken. In the case of the cusp, of course, if you start with very straight lines of the A prime and the B prime, they cross on the sphere. There's not much more than that you can smooth, because they are already very smooth, right? But the radiation, what it does is now wrinkles that lines, which is the opposite of a smoothing. And this is because, back reaction changes the position of the crossing of the A prime and the B prime, but it doesn't affect outside. And therefore, that's why it creates wrinkles. So that's why I'm saying that real back reaction is not exactly smoothing. It has some parts of it, but not. One of the important things it has is that it has the same property that the smoothing has. That if you start with a non-self-intersecting loop and you smooth things, you get to even a better non-self-intersecting loop.
I noticed the loops became more and more square, rectangular.
Okay, well, you should not read too many things from the one loop we showed. That's why I was debating if I should actually show it, but yeah.
I also had a question on Alex Jenkins'
Yes.
Oh. I don't know if he's still.
Don't know.
Yes, but he just wrote he has to
Yeah,
leave.
I think he left, but still we can.
I mean, one.
Oh, Anish, you muted yourself.
I mean, I can raise the question.
Yeah. Yes.
He said something about cutting off the cusp at the Planck scale or the thickness of the string, but really they should be cutting it off at this on this length scale that Jose and Ken, because the sort of cusps are overlapping for a long time. So I think the cutoff should go like square root of the length of the loop.
Mhm.
And I don't think he mentioned.
But I think this is not very relevant in the sense that, as I was trying to explain to him, that no matter what you do, when you want to, once you smooth that very singular point, which is the direction of the cusp, then everything in this radiation looks fine. Because now you don't have that. The total energy is finite. Everything is very small because G mu is very small. So that's why I'm surprised that without any warning, all of a sudden nonlinear effects sort of attack us. I mean, I guess his warning was there is a singularity in the direction of the cusp, but I think this is just wrong in the sense that you can smooth it. I mean, in fact, in the real world, this singularity does not exist because of the thickness or because of the cutoff or the overlapping, whatever, or just wiggly strings that you put in, right? Just any wiggles that you put on the string. So that singularity does not exist. And once you say there is no singularity, then is the total radiation seems to be linear. And I don't see any source of nonlinearities. I understand that he goes, now it takes this as the source to do these other nonlinear effects, and they grow. But that's the thing that I was surprised about, because it seems to me that then I have to doubt any calculation I did before, when everything looked fine, and actually you have to do the nonlinearity to check that it's not growing.
Yeah.
Oh, sorry, there's a big storm outside. If you can see, you can hear strange noises. But so there's one more topic that we wanted to raise. So we invited Ranjan Laha to be another one of our panelists and say a few words about particle and neutrino emission from cosmic strings. Ranjan, are you around?
Yes, I'm around. Yes, okay.
So Anish, do you have a question? You're muted.
You're muted.
Sorry. Yeah. So what I wanted to ask is that I mean, we should not only having gamma rays and the gamma ray constant, since we have so many neutrino detectors, especially high energy neutrino detectors at around this time, or even Planck's in future. So in what possible scenarios we might expect that the neutrinos constraint becoming important than the other gamma ray constraints, and especially the case of Mark Hindmarsh and the hybrid kind of scenario where the particle emissions becoming a bit more important. I think there might be a case. What do you think? I mean, especially the given thing.
Okay, so first of all, I'm not really a cosmic string expert, so I need some help, but I can tell you the neutron and a photon thing. So it's true that what we discussed, that typically photons are much easier to detect, and that's why the constraints from photons are much more constraining. However, there is a catch to this, and the catch is when you go to very high energies. So typically when the photon energy is greater than 100 TeV, what happens is the photons get attenuated. They cannot travel very long distance. And thus, technically, we don't detect any photons, right? For example, at 1 TeV, the mean free path is 10 kiloparsec, right? So that's galactic length scales, right? So at 100 TeV, it's a few tens of kiloparsec, which is not very far away. It's not even Andromeda. So if cosmic strings can emit high energy neutrinos, by high energy I mean energy is greater than 100 TeV, then obviously the neutron constraints will dominate. But as I said, now one of you should take over and say whether cosmic strings can do that or not. I know it depends on the tension. That's the only thing I know. I don't know the numbers.
Yes, especially in the case of the, I mean, hybrid case where you have both kind of situation dominating. I don't know how much this can go, but 100 TeV looks. I mean, what do you think, Tanmay and Mark?
I think it's. I think the answer to your question probably lies in one of these papers in review by Piyush Bhattacharjee and Gunter Siegel, because they were looking into cosmic rays and high energy gamma rays from these TD models, which conveniently could either stand for top down because they're created by decays of massive particles, or topological defects, depending on which audience you were trying to convince. So, and they wrote a very long review in the late 90s, a physics report. And I think the answer to the question is probably in there. But my imperfect memory is that they're somehow, because, I mean, it depends on the details of the particular model into what the string is decaying. But if there's any fraction into standard model particles, then basically nearly all that energy gets processed into gamma rays. Is my memory. But if you can suppress that channel, then and leave the neutrinos, then it may be that the neutrino constraints are stronger.
I think the standard thing to do is to imagine that this heavy boson decays into something that, like quarks, that hadronize and produce pions, and therefore you basically say that you produce photons because the pions decay and the pi plus minus also produce neutrinos. So by doing that analogy with something that we know in the standard model, you get some fraction of the energy into neutrinos. Of course, this is all based on analogy. And is there any idea how the spectrum might look like, the spectrum of neutrinos coming from the? Well, they also use this same argument. They say everything because of this sort of shower that I just explained, everything depends on what is the fraction of energy that each quark takes from the original boson, and they take inspiration from the Z0 decay. I see. Okay. And therefore, the thing at the end is the power law. I see. Okay. If I recall correctly, it's a power law like E2 minus, I don't know, E2 minus something. It's 2, maybe, I don't know.
I don't remember.
Okay, well, it's actually 6 past 9 p.m. So we're a little bit after the official closing. So let's I'll close the session for now. The room will stay open in case you want to discuss more. But this is the end of the official part for today. So thank you all for attending.
Thank you.
Thanks for the host.
Thank you for hosting.
Thank you. I stopped recording.